This is the lecture on the principle of linear superposition, and we will be looking at constructive and destructive interference of light waves and how they can allow for patterns of light to exist. Here you'll notice that there are two sources of light. Here's source 1 and here's source 2. They each are sending out a wave, and the waves emitted by source 1 and source 2 start out in phase and arrive at point P in phase, leading to constructive interference at that point. This is very similar to the constructive and destructive interference of sound waves we did a while ago. So you'll notice that in source 1 it's 2 1/4 wavelengths, in source 2 it's 3 1/4 wavelengths, so the difference in their lengths is 1 wavelength, therefore you have constructive interference. If the difference in their lengths was half a wavelength, you'd have destructive interference. So here is our example of destructive interference. You'll notice that they're in phase, but the source 1 has a wavelength of 2 3/4 wavelengths. Source 2 is 3 1/4 wavelengths. That's a half wavelength difference. Therefore, destructive interference will occur at this point. So the light wave will cancel each other out, and it'll be a dark spot right there. If constructive or destructive interference is to continue occurring at a point, the sources of the waves must be coherent sources. Two sources are coherent if the waves they emit maintain a constant phase relation. This means that the waves do not shift relative to one another as time passes. They keep their wavelengths, they keep their frequency the same the whole time. What we are now going to look at is called Young's double slit experiment. What Thomas Young did was send a light into a single slit. What this single slit did was make a beam onto a double slit. And what you have here, though, is these areas of constructive, where you see the white, and then destructive, where you see the black. Actually, this is yellow. And destructive, where you see the black. So you have the bright fringes and the dark fringes. Where the bright fringes are is constructive interference. Where the dark fringes are is destructive. So you'll have 0 wavelengths difference between the two slits, 1 wavelength difference, 2 wavelengths difference, 3 wavelengths difference. And then for destructive interference, you would have half a wavelength, and then you'd have 1 1/2 wavelengths, and then you have 2 1/2 wavelengths. This constructive and destructive interference of light waves is exactly the same as the constructive and destructive interference of sound waves that we studied earlier. Here we have a setup that shows the double slit diffraction grating here. You'll have one slit here, one slit there. There's this variable D, that's the distance between those two slits. The variable L is the length from the slits to the screen where the light is falling. And the light is coming in. This is violet light coming in. You have light coming from this source and from this source. So now you have two sources, and over here you have your destructive and constructive interference pattern. You'll notice this is the screen right here, and so there's a constructive, destructive interference. And the wavelength, and this graph here is this shows the intensity of light. So here where there's constructive interference, it's a very high intensity of light. Destructive interference is a very low intensity of light. So here are different ways I could change the variables. I'm going to change the wavelength of light. I'm going to change from a small wavelength to a large wavelength where it's red. And you'll see that this distance here from one constructive interference point to the next constructive interference point is longer now. This variable here is actually called x. I'm going to put it back to, let's put it back to green light, let's say. And now I'm going to change the D value. You'll notice this D value right here, the distance between the slits, as I make it larger, you'll see that the X value becomes smaller, and as I make the D value smaller, that X value becomes larger. The distance between the constructive interference points just became larger, and when I made D larger, the distance between the constructive interference points became smaller. So there was an inverse relationship there. So I'll put it right in the middle for now, and now I'll change length. I'm going to change this L value, and as I increase L, you'll see the distance between the constructive interference points increases. So that's a direct relationship. Smaller, the x value becomes smaller, L becomes larger, the x value becomes larger. So that's a direct relationship. And then the lambda was a direct relationship as well. As the wavelength became larger, so did the x value, so did the distance between the constructive interference points. So what happens is in the Young's double slit experiment, the two slits S1 and S2 act as coherent sources of light. Light waves from these slits interfere constructively and destructively on the screen to produce the bright and dark fringes. Here is a top view of slit 1 and slit 2 meeting at the middle here for constructive interference. And now we see that we have another point of constructive interference, and this second line here is the same length as the first line, but it's one wavelength longer to have the constructive interference. And you'll see that that extra length right there is that one wavelength. And it forms a triangle, you'll notice, right here. And it's approximately a right triangle. It's not exactly, but it's pretty close. Where the destructive interference point occurs is a half wavelength increase in length, and that extra distance there is a half a wavelength. And what this picture shows is that there's this right triangle that I talked about earlier. We're going to talk about constructive interference here, and there's some variables. This is your right triangle, and there's these angles here. There's this theta angle, which is just basically the angle between this position and one of the constructive interference points. It happens to be the same angle as this little triangle here as well. And so what that triangle leads us to is this equation. Sine theta equals m wavelength over d for bright fringes of a double slit diffraction grating. And for dark fringes, sine theta equals m plus a half wavelength over d. And that adds that half wavelength. So you'd have the destructive interference. This equation works in any situation. Sine theta equals m wavelength over d. And m equals 0, 1, 2, 3. That's the bright fringe spots. This is the middle bright fringe, this is the first bright fringe, second bright fringe, and so on. So looking at a possible problem we might answer, red light has a wavelength of 664 nanometers in vacuum. It's used in Young's experiment with the slits separated by a distance d of 1.2 times 10 to the negative fourth meters. The screen is located at a distance of L, 2.75 meters from the slits. Find the distance y on the screen between the central bright fringe and the third order bright fringe. So we want to find that y value, the distance from the central bright fringe up to the third order bright fringe. Here is a picture of that situation. We have our D value shown, we have our L value shown, and here's our Y value that we want to solve for. Here's the M equals 0 bright fringe, and there's an M equals 1, and an M equals 2, and then now they're showing the M equals 3 bright fringe. So the third order bright fringe has an M value equaling 3. It's observed on the screen at a distance Y from the central bright fringe of M equals 0. So this is what our picture looks like. If we now use our equation, sine theta equals m wavelength over d, we solve for theta and end up with an angle of 0.951 degrees. Usually, many times our angles are very small in these problems. But they wanted us to solve for the y value. So what we're going to do is go back to that triangle and realize that if we look at this angle right here, tangent theta equals opposite over adjacent, so it equals y over L. So now we have this tangent theta equation, plugging in all our values. We see that that distance from the central bright fringe to the third bright fringe is 0.0456 meters. So in this lesson we learned how to recognize the variables of a diffraction grating setup and the equations that we'll use to help us solve problems.